So welcome students to video class 35, and we are continuing our discussion on Nyquist stability criterion, and this is part 2. So far we studied basically in the last video we concentrated more on two aspects. One is the principle of argument, the other one is the Nyquist stability criterion. Okay, now what is this principle of argument? So the principle of argument is a general statement regarding any closed contour of any plane, of any complex plane. So here the complex plane is the S plane. Okay, and we already know that. So this is an S plane for you. We already know that the thing which causes the instability is the poles residing in the right half. So all the methods so far we studied, actually it checks in different ways whether there is any right half poles is present in the or poles present in the right half of the S plane. So our interest is always on the right half, okay, or our concern is basically on the right half of the S plane. So for any chosen, so this is just a general statement of any contour. For any chosen contour in S plane, if the mapping function f of s is analytic at every point, the f of s. So what is the meaning of analytic? Analytic already you have studied. That is, it simply means f of s is differentiable at every point. So that means, suppose you had a mapping like this, you will be getting a different picture of this. So what you did is you have formed a closed contour of your concern. That is the whole right half plane. That has been mapped. How will you map? You will be mapping by by substituting all the values into this f of s, so that you will get a different picture. When you plot this f of s over here, you will get a different picture. So this is how mapping is done. Now, so mapped into this function g of s, mapping is done at every point. This f of s and the picture is going to encircle at the origin. So here is the origin for you, and this will be encircling the origin as many times as the difference between the number of poles and zeros of f of s. Okay, it is the number of poles and the difference between number of poles and zeros of f of s encircled by this s contour. That is very important. That is enclosed by the s plane contour. Okay, so f of s that are enclosed by the s plane contour. So we are worried about whether there is any poles and zeros. So this will give you the number of encirclements, will give you what it is. The there will be as many number of, right, as many times there will be encirclement based on the difference between the number of poles and zeros of f of s that are enclosed by the s plane contour. Hope you understood. So this s plane will be, so what we need is, we want to know whether there is any poles inside this. So this encirclement will give you the if the encirclement is 0, that means both p and z are equal. I mean, there is no, the difference is 0, right? If there is encirclement, if there is 1, then the difference between 0 and pole will be equal to 1, and it goes on like that. Okay, now what we need to find out is how to use this principle of argument for our stability, and that has been used by, called as the Nyquist stability criterion. For applying this criterion, what we do is the entire right half of the S plane is mapped into, as shown here, mapped into a mapping function g of s h of s. So what is its origin? The origin is denoted as 0, right? This is your origin of this, if you consider this f of s as your g of s h of s, right? But our main aim is to find out what? Find out the right half plane, right half poles of 1 plus hs gs is equal to 0. Okay, so what is the difference between this gshs and 1 plus gshs? Only difference is that you will be having the same picture. The difference is, instead of this origin, you need to consider this minus 1 as the origin. Okay, now, so that is the relevance of this minus 1 plus g0. So whatever, I mean, you will start with gshs and you will obtain the contour. Then you will consider this minus 1 point and see whether this picture encircles this minus 1 plus j0 point. So that is the significance of minus 1 plus j0 in Nyquist stability criterion. Now, as per the principle of argument, the resulting contour will have as many as the difference of right of poles and enclosed by the S contour, right? So when you consider this minus 1, and if you find number of encirclements to be equal to say 1 or 2 or whatever it is, so that says that this is equal to the difference of the poles and zeros enclosed by this S plane considered, that is the right half plane, right? So you will get an equation like this: n is equal to z plus minus p plus. What is this p plus? Plus refers to right of poles. Z plus refers to right of zeros. So this is equal to the right of zeros minus right of poles. So this information you will directly get from this GSHS. Okay. Now once if you get GSHS, suppose you imagine that your GSHS is equal to something like this, say s plus 3 divided by s minus 2 into s plus 3, s plus 4, right? S plus 4. So you know that when you calculate the poles, you know that one pole resides at s is equal to 2, one is at s is equal to minus 4. So how many, so you will get the p plus from this. P plus is equal to 1, right? This is your p plus. This is the right half poles, right? So the number of p plus is equal to 1, right? Now, using, so suppose this is your GSHS. Now using this method, you can map the whole S plane, right? This right half plane to this function, and you will be getting a contour. Okay. Now from that contour, you will be getting the information of what? Information of the number of encirclements on minus 1 plus j0. Why? Hope you understood why I have taken minus 1 plus j0, because actually our concern is not GSHS. We want to know about 1 plus GSHS. So from GSHS itself, we will get the information regarding 1 plus GSHS. The only thing is that you need to consider the origin to be at minus 1 plus j0. So from this you will get the n, already got p plus. Now from this you will be able to get z plus, right? So from the principle of argument, right? So this z plus becomes equal to n plus p plus, right? N plus p plus. And when you evaluate this, you need to get this as to be equal to 0 for the system to be stable. Okay. Now what is the logic behind this? Now yesterday also I have defined this. Now this is the z plus of what? It is not the z plus of GSHS. Because we have selected minus 1 as the origin, this is directly becomes the z plus of what? 1 plus GSHS. So I have told you already, 1 plus GSHS, when you equate to 0, you will get the poles of the closed loop system. Okay, this is the poles of a closed loop system. Why? Because the closed loop system transfer function is given by 1 plus GSHS, right? So when you equate this to 0, so if you can consider this function as P of s to Q of s, you are equating P of s to Q of s to 0. So in a sense, you are equating P of s to 0. So as far as a characteristic equation is concerned, this is the zeros. This is, so P of s is equal to 0 gives you the zeros of what? Zeros of the characteristic equation. So when I say the poles of this closed loop transfer function, I mean right half pole, there should not be any right half poles for this closed loop function. What I am saying is there should not be any zeros for the characteristic equation. So that information is what you will get from the Nyquist stability criterion. And if it is equal to 0, then you can say that the system is a stable system. Okay, so you'll understand this when we do problems. Okay, now since the Nyquist contour, or this diagram we call as a Nyquist diagram. Now from the Nyquist diagram, we need to find out the encirclement. I'm just showing you an example how to find the encirclement about a point. So here you have 3 points. So do remember, when you apply Nyquist criterion, our point of concern is minus 1 plus j0. I am just doing it As an example, I have considered an origin O, then you have A, then you have B. How to find out the encirclements? So imagine that this is the Nyquist diagram that you got. So you don't have to worry about how to obtain this Nyquist plot. That I will explain when we do problem, how to convert or how to map or how to get the mapping of this entire S-plane to GS, HS or whatever it is. So imagine that you got a plane like this. How to calculate n? That's the primary thing that you require after getting the plot. So that you should understand very well. So far in our maybe in our SFG and all those things. Sorry. So by convention, what we do is the anti-clockwise direction is taken as positive, while clockwise is taken as positive. Here the encirclement can be both anti-clockwise and clockwise. Here anti-clockwise is taken as negative, okay, while clockwise is taken as positive, okay. And that's how this formula is expressed. Z plus is equal to n is equal to Z plus minus P plus. So anti-clockwise direction has to be taken as positive. Now when you consider this O, how many encirclements this has? One is this. The direction is important. Now how will you put this direction? That all you will understand when you draw the Nyquist contour. Okay, for the meantime you don't have to worry about the figure or the picture. I will give you an information, a clear idea how to draw this later in the session. Now this is actually, so this one regarding this point, this is one of the encirclement. Now this is a clockwise encirclement, so that is one encirclement, right? Now there is one more encirclement. See, okay, this is something like this, right? So when you start from this point, the encirclement, how will you identify the encirclement? Starting a point and you will reach at that point. So this is one encirclement, and another encirclement is you can say start like this. Okay, this is another encirclement, right? So in the origin you will be having 1 plus 1, which is equal to 2. Now what about the at point A? At point A, when you look at this, you can see that there is an anti-clockwise direction, so that is 1 is minus 1. Then this big encirclement is anyway, this is inside, or this is revolving around A as well. So you have this A is also having one more encirclement, but that is in the clockwise direction, so that is equal to plus 1, which is equal to 0. Now what about B? B is also having a clockwise direction, so this is having a clockwise direction, right? Clockwise direction. So the encirclement is like this, right? So you have a plus 1, then you have a big encirclement as well. So you have plus 1, which is equal to 2. Okay, so this is how you need to find out the encirclements, okay, around a point. Hope you understood. Okay, so here is a question for you. An open loop transfer function of a negative feedback system is given by a GSHS is equal to K by S into S plus 2. Draw the Nyquist diagram and check for the stability of the system. Okay, so when you are asked to draw the Nyquist diagram itself, it is obvious that you ought to apply Nyquist stability criterion, and that is how you need to check the stability of the system. So do remember, the Nyquist criterion is nothing but we need to make that Z plus to 0 for the system to be stable. So that is what we need to find, whether that Z plus is 0 or is it having any values. So if there is any value, that refers to the fact that that gives you an idea about the number of right of poles of the characteristic equation residing in the S-plane. Okay, to start with, we know that the number of encirclements of the contour that we are going to draw must be equal to Z plus minus P plus. And we have already defined this P plus to be what? P plus is actually the number of poles of this G of S H of S which resides at the right half of poles. So that is your step 1. You need to find out the number of right half poles of G of SHS. That is, from this equation, one thing must be known from the given open loop transfer function. So you need to find out P plus. Now just find out the poles. The following are the poles. One is S is equal to 0. The other one is S is equal to minus 2. Right? Okay. That is, you can say that there is no right half poles, that is P plus is equal to 0. Okay, so this is step 1. So this is the result obtained after step 1. So one thing we have found out, right? Another point that we need to find out is from the contour. That's the next step. And from these two information, you will be able to identify what is Z plus. And so next step. Now, the next step is to identify the Nyquist contour. Okay, identify the Nyquist contour. Okay. Now, what is this difference between Nyquist contour and Nyquist diagram? Nyquist contour is actually the right half plane, the right half of the S plane. Okay, so you need to identify that Nyquist contour. So every time it is going to be the right half, then you may be thinking, then what is the need of this step? You just need always the S, it is the right half of the S plane. So what is the meaning of contour? Contour is just the path traversed by from one point to the other. That's all. So, okay, it just refers to the path. So the path of our concern is we need to map what? We need to map the whole of the right half of S plane. Okay, so that means this is going to be your, so I'm just using a dotted lines only because this has the what is going to be its boundary. Whole of right half means if I consider the radius, this is the big radius, say I'm calling this as R. What is going to be this R? So R tends to infinity, because this must be the whole of our right half. So I am concerned about the right half. I am concerned about the right half poles. So I need to consider the whole of the S plane. This is what I am going to map. This is what I am going to map into the function GSHS, right? Or f of s. Okay, so what you need to do is you need to get the contour, the contour of your concern, right? Or of your interest. That is what is called as a Nyquist contour. Now this is an S plane, right? But when you draw the Nyquist contour, so you may be thinking that okay, then for every problem this will be the step 2 will be always the same. The contour diagram will be always the same. The answer is no. Now here in this example, just before drawing this, you must find out the type of the system. What is the type of the system? The type is equal to 1. Now the meaning of that is you have a 0 at the origin, right? You have a 0 at the origin. You have a pole at the origin, you have a pole at the origin, right? So if you have a pole at the origin, what you need to do is you need to exclude that point. Now this is your contour. Basically this must be your contour, right? This is your contour, right? You must draw it equidistantly. This must be equal. This and this has to be equal. But the thing is that why do you exclude this? The pole at the origin, anyway, it is referring to a marginally stable condition. So we just want to know about the actual thing which causes the instability. So because of the fact that we always exclude the poles that resides on the imaginary axis. So since it is a type 1 system, we know that there will be a pole at the origin, so we need to exclude that. Okay, so this is how it goes, right? And moving on to the contour, let us see the direction of this contour. Okay, now the s actually starts from here, but at s is equal to 0 you need to exclude that point. So I am marking this point as, say, some 0 plus. It is a point just above 0. That's the meaning. I'm just excluding that point. Now you cannot show it in a figure, that infinitely small point. So that's why I'm considering this point as 0 plus, just above 0, right? So what must be this point? So this is whole of the right half, means this has no boundary. That means this has to be, this represents j infinity plus, right? And it meets over here. What is going to be this point? This has to be j infinity minus. Okay, so minus j infinity, this is plus j infinity, right? So this is the, because these two limits have no boundary. And now when you look at this, you have a direction, right? It is 0 plus 2, right? This is the direction, so I'm going to mark that direction as, this is 0 plus 2 j infinity plus. Now from j infinity plus to j infinity, you have another segment. You can divide, you can consider this as then you have a minus j infinity to j, and what must be this point? This is also some 0 minus, right? This is 0 minus, so you have a 0 minus. Then at the 0 minus to 0 plus, you have one more direction. So look at this, the direction that I have shown. You have a clockwise direction, since I'm starting from 0 plus, and it should come at this point. So as you move in this direction, this is a contour, this is a path. As I move through this path, I can identify the direction in this way. Okay, so as I have traveled, I have identified 4 different segments for this contour. Okay, as per the direction, right? So one segment is, I'm calling this as, say, at 0 plus, this as A, this is B, this is C, and this as D, right? So you have a path like this, A, B, C, D, A. This is the path traversed by this S-plane, right? Now, let me tell you, let me make this into segments. Now, what all things you need to map? You need to map this to in the next step, what you need to do is you need to map this to a function f of s, g of s, h of s, or f of s. So in order to map this, what I'm going to do is I'm breaking this whole contour into various segments. So segment AB, right? Okay, so that's a line segment, straight line. Then that's a line segment, right? Then you have a BC. Okay, now BC is not a line. BC is a infinitely radius. It's a circle with infinite radius. So this is a circle with R, capital R, tending to infinity, right? Now coming to CD, I'm breaking this into segments. CD is again a line segment. Okay, now more on this AB and CD. Now the line segment AB starts from 0 plus to j plus j infinity, while CD starts from minus j infinity to 0 minus. Am I right? Then you have DA. And what is that? That is again a circle with small r. So this can be considered as a small r. It's having a radius small r, but that is more close to 0. So you have identified 4 different segments over here. Okay, now suppose if there is no S term over here, then what will be your contour? What will be your Nyquist contour? The Nyquist contour will be the whole of S plane, right? It's something like this. That means you don't have to exclude any point because there is no pole at the origin. So this will be, you will be having only 3 segments, right? That is 0, A, B. So what will be the possible segments? It will be 0, A, O, A. Then you have an AB circle, big circle, and a BO segment. Okay. Now, I'll give you one more thread. Now, while mapping, what you are doing is, in the next step is, you will be mapping each segment to this given GSHS. Okay, so you will be getting a different picture. Now, to make things simple, what I'm telling is, this line AB. Look at this line AB. This line AB and CD is having a relationship, right? This is a mirror image. So the mapping of AB will be exactly the mirror image of ZD. So you don't have to again map CD. Once if you get AB correctly, you just need to draw its mirror image. That's enough for this. Okay, so that makes this a bit simpler. Okay. Next step is to obtain the Nyquist, obtain the mapping. Okay, obtain the mapping, or to perform the mapping from the specified S-plane or the S-plane of concern to GSHS, which is considered to be your f of s, right? So you need to map this. Now, how to map this? That's the next issue. So before mapping, you have some steps that is to be done. That is, find out S is equal to, put S is equal to j omega and obtain the sinusoidal transfer function. So the sinusoidal open loop transfer function becomes g of j omega into h of j omega becomes equal to k divided by j omega into j omega plus 2, right? Now, the next step is, so this is step 1, sub-step, okay? Next is, putting s is equal to j omega, it's get converted into a sinusoidal transfer function, right? Now, after finding out the sinusoidal transfer function, the second step is to convert it into magnitude polar form. Okay, now how to find out the magnitude polar form? So just take the magnitude. So this is of the form, say, a plus jb divided by c plus jd. Okay, if this is of the form, convert this into root of a square plus b square into tan inverse b by d divided by root of c square plus d square tan inverse c d by c. You can divide this, right? Magnitude is to be divided, angle is to be added or subtracted, whatever it is. Okay, so you are converting that into, so using that, what is the magnitude of k? K is a constant, therefore the magnitude is k itself. What is the magnitude of j omega? J omega is root of omega square, which is omega. What is the magnitude of this thing? This will be root of omega square plus 4, right? Right? And what about the angle? The angle is tan inverse of 0. So this is the angle corresponding to this is 0 degree. The angle corresponding to this is 90 degree. Angle corresponding to this is tan inverse omega by 2, right? This is tan inverse omega by 2. So what you learned in the angle is numerator angle minus the denominator angle, so that you will get this as minus 90 minus tan inverse omega by 2. Okay, now this is the expression. So this is actually your magnitude of j of j omega, h of j omega, angle g of j omega, h of j omega, right? So you have got this into a polar form, right? So obtained this into a polar form. Now we are going to so we have already segmented, right, AB. Now the first step is, we'll have to start from AB, right? Because A is the point where omega starts. It is 0 plus to j infinity. So when you consider AB, this is actually a line segment where omega varies from 0 plus to j infinity plus, right? So I got 2 points for omega, that is 0 plus and j infinity plus. Now you can simply find out what? Find out this. So find out this j of j 0 plus h of 0 plus is going to be equal to what? You put omega is equal to, so at first omega is equal to 0 plus. So when you put that, you will get this as 0 into root of 0 plus 4 angle minus 90 minus tan inverse 0, which is 0, right? So tan inverse 0, which is equal to 0. So you will be getting this as infinity angle minus 90 degree. Okay, infinity angle minus 90 degree. Now similarly, you can also plot g of j infinity plus h of j infinity plus, right? Or infinity. Okay, that is, you don't need to put j, because omega, we just need to put omega. Omega is equal to infinity plus, right? So when you put infinity plus, you will get this as k by infinity into root of infinity square plus 4 into tan inverse, right? Okay, so what is this? Angle tan inverse, sorry, angle minus 90 minus tan inverse infinity. What is tan inverse infinity? That is again minus 90. So you will get this as, what is k by infinity? K by infinity is 0, angle minus 180 degree. Okay, so what you understood was, say, as your omega varies from 0 to infinity, the amplitude, it's having a magnitude at infinity, but it is showing an angle minus 90 degree and minus 180 degree. So do remember, see, you are to plot this f of j omega or f of omega, or you are going to have the Nyquist diagram. Okay, the first part of this question. So now you want to find out this. See, at omega is equal to 0 plus. So when we mapped this segment, we have seen that the magnitude is infinity, right? It is infinity, but it is at an angle minus 90 degree. So already I have specified, always the angle, the clockwise angle has to be taken as positive, negative, anti-clockwise has to be taken as positive, right? Except in the encirclement part. Okay, do remember, in the encirclement you are doing it in the reverse way. In all other problems, even when we did root locus and so on, right, we always consider the anti-clockwise direction as positive, and clockwise angle has to be taken as negative. Here also, when you plot this, this has to be taken as the clockwise direction. So what is 90 degrees? If this is 0 degree, if this represents 0 degree, this is minus 90 degree. Okay, this is actually 270 degree. When you so this is actually 0, 90, 180, okay, and 270. So this is actually minus 180, and this will be minus 270. Okay, right, in this direction, in the clockwise direction, this will be the angle, right? So anyway, we know that this is having an so when we plotted omega is equal to 0 plus, we found out that the magnitude is infinity, and it is having an angle of minus 90. So this you can represent like this. You cannot touch this because this touches only at infinity. Magnitude is infinity, but the angle of that plot is minus 90. That means this is at minus 90. Now what is the next thing? Next thing, as omega reaches infinity, what we found out that the magnitude reaches 0. 0 is the point over here, but the angle, it seems to be minus 180 degree. So one can think, say, I'll be using a pencil, right? One can think in this way. Say it starts from over here. We found out the starting point, and the ending point, say something like this. A plot can come over like this to this point. Anyway, we have identified the point. The point corresponding to infinity plus is this. But this plot can come in this way. Now this plot can go in this way, right? Okay. So we do not know whether it stays or it can also come in this way, right? Now how this travels, that's what we need to find out. Anyway, what we understood is minus 90 and minus 180 degree are the angles in the third quadrant, right? So we got a feeling that this plot always remains in the third quadrant. In order to prove that, we need one more point. So I'm just putting this as j is equal to 2. That is, just I'm substituting omega to be 2. So when you plot that 2, you will be getting that as, okay, k by 2 root 8. Okay, so it will be k by 2 root 2, but the angle becomes minus 135 degree. Now from this we understood that this minus 135 degree comes in between this, right? This is minus 90, this is minus 180. That means this point also, so omega also, so that means this particular plot is not going over here. Why? Because there is no angle, the maximum negative angle is minus 180 degree. So this plot should remain in this direction. So you can plot that by hard line. Okay, so this is the point corresponding to the line segment AB. That is, this is the point when we mapped omega is equal to 0 plus. This is the point when we plotted omega is equal to infinity plus, right? So that's the point. Now let us see what is going to be the, so you can also straight away find out the CD segment. What is the CD segment? So as I've already told you that this CD segment, you don't have to do this. Anyway, the CD segment is exactly the mirror image of this. That means you're going to get like this, right? Right? So what is the first point that is to be plotted? That is j infinity, minus j infinity to, so it will be plotted in this direction, minus j infinity to 0. So once you, so this is again a point corresponding to j infinity minus, and this is the point corresponding to 0 minus, right? Okay. Okay. So you'll have to mark the point. So it is plotted in such a way that 0 to infinity plus, and j infinity plus to j infinity minus to 0, and it goes on like this. Okay, hope things are clear. Now the next segment that is to be plotted is the big circle BC, right? Okay, so look at this. So we have so far plotted this segment A to B and C to D. Okay, now we need to plot this segment, this big circle, and the big circle is defined as, it's a circle with r tends to infinity. Okay, now you can you can represent a circle by the equation r e raised to j theta, right? R e raised to j theta. Okay, so this is r e raised to j theta. Now since it is a clockwise direction circle, I am putting it as r e raised to minus j theta. It is a clockwise circle, right? So I am putting it as r e raised to minus j theta. Do I again emphasize the point? When you consider the encirclement, you need to take anti-clockwise as negative, clockwise as positive. Now this is r e raised to minus j theta, and you can define the circle as it is r tending to infinity. So this is actually a definition of that big circle. So in this, while mapping this, you can use the straightforward, you can use the basic equation which you got from your question. That is, put S is equal to this thing. So when you put that, k by r into e raised to j theta, r tends to infinity, into r e raised to minus, okay, minus j theta, okay, r e raised to minus j theta plus 2, okay. Now, since r is infinity, r is a very large quantity, you can ignore this term, so that this becomes k by limit r tends to infinity, okay, this is r square e raised to minus j to theta. So this 2 has no relevance anyway, this just represents the angle, okay. So this will be k by r square limit r tends to infinity e raised to plus j theta to theta, right? Plus j to theta. That means what is this? This, when you apply the limit to r tends to infinity, this becomes a 0 e plus j theta. So what is the meaning of this? This is the big circle, which is the BC, has been mapped into a very small circle with the radius 0, right? With the radius 0, almost to 0, with an anti-clockwise direction. Now let us see, will you get an anti-clockwise direction in this? Okay, now when you plot this, this becomes a very small, how to plot the small circle? This comes to a point, right? Now if you can assume there is a small circle, something like this, in order to restore the direction, look at this. The direction you must be, the circle must be in the anti-clockwise direction, then only it will be proceeding like this. Suppose imagine that this is in the clockwise direction. This direction will not match with the direction of this circle formed. Now when you look at this, if you can assume a small circle, you can see that it is a continuation of this contour, right? This moves in this, and it is going to be an anti-clockwise circle. But anyway, you don't have to specify that. You can just consider as a point, because upon mapping, this big circle reduces to a point. That's the meaning of this. Now what will be now the last segment that you need to, that is DA. That is a DA. So what is DA? DA is again represent that as a, since it is a very small circle, and representing that by r e raised to minus or plus j theta. That's what we need to find out. Look at this. This is anti-clockwise direction. This is how the direction is shown, right? This is anti-clockwise. So this must represent a small r e raised to plus j theta, right? R tending to 0. So this is r e raised to plus j theta, r tending to 0. This is your s. Put s is equal to limit r tending to 0 in this equation. So upon substitution, you will get this as limit r tends to 0, r into e raised to j theta into r e raised to small r e raised to j theta plus 2, right? And since this is r is very small, what happens is r is almost equal to 0. You can neglect the value of this in comparison this 2, so that this becomes k by 2r e raised to j theta limit r tends to 0, or this will be k by 2r into e raised to minus j theta, right? Now upon limit r tends to 0. Now when you apply the limit, you will get this as infinity e raised to minus j theta. So what is this? This shows that this small circle is mapped. So the small circle which we have mapped, that is this small circle which we have excluded. Why we have excluded? Because there is an origin in the open loop transfer function. So we have excluded because that is not taking part in the complete instability of the system. So the point correspond, or the circle, when we map the small circle, we've got a big circle with infinity e raised to minus j theta. Now look at this. The starting point of this circle is at the tip of this 0 minus, right? And it ends at 0 plus. So in that context, if you draw this, now what is the 0 plus, 0 minus corresponds to? 0 minus is a point over here, right? Now this is 0 minus to 0 plus. So you need to draw in that direction itself. So this is the point corresponding to 0 minus. You need to show a big circle to 0 minus, right? Okay. Now, so this is how the circle. So you need to draw in this way. Show this is a big circle. Big circle means it's not a, you can draw that by dotted lines. Say, okay, this I have just used, this is not right anyway. Anyway, you need to draw this by dotted lines. Use dotted lines. Why? Because this is not a finite quantity. It is anyway, r tends to infinity. So it moves in this direction, right? It moves in the clockwise direction. So this is the direction. This moves in this clockwise direction. So you may be thinking that why can't you plot in this way? Why I hadn't plot in this way? Okay, why this is plotted in this way? So look at the equation. It is infinity e raised to minus j theta. We have assumed e raised to plus j theta as the anti-clockwise. So this must be a clockwise circle. Now had it been in this way, it must be a anti-clockwise direction, right? So since the circle produced has to be anti-clockwise, you need to draw like this. So you got a graph something like this, right? Okay, so this is what is called as a Nyquist diagram. Okay, that is Nyquist diagram, and that is your step 3. Okay. Okay. Now the step 4 is, after obtaining the Nyquist diagram, find out the encirclement at minus 1 plus j0. That's what the Nyquist criterion says. The Nyquist criterion is concerned with minus 1 plus j0 because we have drawn this for GSHs, but we want the plot to represent what? 1 plus GSHs. So the origin, this origin has to be moved over here. So this is minus 1 plus j0, right? And we need to find out the number of encirclements that this Nyquist diagram makes around minus 1, 0. Anyway, the figure itself shows whatever may be the value of omega, this diagram shows that this is not going to encircle this point minus 1 plus j0. So what is your encirclement? The encirclement is 0. Okay. Now, from this, don't conclude that the system is unstable. Now, what is this Nyquist criterion says? Nyquist criterion says for the system to be stable, Z plus has to be equal to 0. That's what we need to find out. Okay. Now, we have already, now coming to the step 5, that is the ascertaining of the stability. So, the step 5 is the comment on the stability, or comment on the stability. That is, now you are to apply apply the based on the principle of argument. We have a Nyquist criterion as n is equal to Z plus minus what? P plus, right? Now this P plus is 0. We know that P plus is equal to 0. We know that n is equal to 0. So what is your P plus? P plus is also equal to 0, meaning that what is P plus? P plus is the right half poles. The right half poles that is being encircled by, or that is being enclosed by this S-plane, which we have considered. Okay, so P plus is nothing but it is the number of right half poles of the characteristic equation, or 1 plus GSHs, enclosed by this S-plane, and we have found out that to be 0, right? Sorry, this is Z plus, sorry, Z plus, right? P plus is 0. So once you get it, Z plus is 0, this refers to the number of right half poles of the characteristic equation on the right half of this plane, which is found to be 0, and that is the condition for stability. So the system is a stable system. Okay, the system is a stable system, right? Now it is also independent of the value of k. Whatever may be the value of k, okay, whatever may be the value of k, the picture is going to be like this. So this is not going to encircle the point. That is, this is totally independent of k, or in other words, this is a stable system. This is a stable system for all values of k. For all values of k. Okay, that's it.